I can't express, it's difficult for me to express how much joy it makes to be here introducing Nikhil. When I think about Nikhil, we go back to 2012 where we were grad students together in Matt Mason's lab. Actually, Matt is right there in the computer. And it was back then when we started talking about this idea that thinking about dexterity as something that happens within the hand, it was very limiting, and to some degree it could be be damaging to the notion of dexterity, for it to be so constraining. And I don't know who convinced who, but after a while we came almost at the same time to MIT, and we decided to work on that idea together to push it forward. Actually, we opened our lab together at the same time. So when I think about my time here at MIT, it's impossible to disentangle it from my time with Nikhil. It's the same trajectory. So one of the things that I would highlight about Nikhil's PhD thesis is that it's probably one of the best examples of obsession about one particular idea, is that initial idea about pushing forward, demonstrating that dexterity can be something that is much more, but at the same time, much simpler than the general notion that we have in robotics. And I'm very happy for him to be here today to explain that story, which I think is a very nice story. Thank you, Nikhil.
Okay. Thanks, Alberto, for that very generous introduction, and thank you all for being here for my thesis defense. Today, I'll present some of my work on dexterous manipulation with simple grippers. So it's not always possible for robots to pick up an object in a pose that is directly useful. I'm interested in enabling robots, even those with simple grippers, to regrasp an object in hand so that they can use different objects effectively at the desired applications. I can explain my approach to such dexterity with this view from the camera that's in the palm of the gripper. It provides gripper's perspective. The key enabler for the dexterity is this one special finger that is fully actuated, and it has 6 degrees of freedom. It has 3 rotational freedoms and 3 translational. It has a very large workspace, and it can be very fast and precise. So this dexterous finger can then move the object in the grasp by pushing it from different sides, while the other fingers hold the grasp securely. So notice there's something different about this finger. It's not only independently controlled, it's actually detached from the gripper. So what's this special finger? It's actually a fixed finger in the environment, and all the motions we saw before are just the reflections of the robot's motions against the fixed environment. This shows that how simple features in the environment combined with robots' motions becomes dexterous fingers that all robots actually have. And then we can use these dexterous fingers to move the object in the grasp and manipulate it very dexterously. And it's not just these external contacts that can help robot to manipulate objects in the grasp. Robots can think about using gravity and their dynamic motions to manipulate objects in hand. And that's how my work on in-hand manipulation actually started at CMU. There, I showed that using these external resources, such as gravity, dynamic motions, and external contacts, simple robots and with simple grippers can do these in-hand manipulations very reliably. We called it extrinsic dexterity. All these primitive actions they were hand-scripted and hand-tuned. The goal of this project then was just to show the mechanical feasibility of these actions and understand their robustness. The motivation to explore extrinsic dexterity, it naturally comes from observing how we humans and even animals around us manipulate objects. We actively use gravity, dynamic motions, and even contacts with the environment to effectively manipulate objects in hand. In all these cases, we are able to do these in-hand manipulations very reliably, fast, and with simple simple actions. Interestingly, using such external resources for object manipulation has been explored in the robotics community. Here, we see the examples of using gravity, dynamic motions, and external pushes to manipulate objects in the environment using simple mechanisms without even grasping the objects. But when we see the work in prehensile manipulation, that is manipulating a grasped object, most of the work, starting from early days even until now, is focused on designing these human-like grippers and using them. It's commonly known as dexterous hands approach. The idea here is to move the object in the grasp by controlling the fine motions of the fingers. This approach has actually led to very interesting results for in-hand manipulation. But designing and controlling these complex grippers is a very challenging problem. And these grippers are extremely expensive. So with lack of simple, cheap, and reliable solutions for in-hand manipulation, the problem is often, it's modified so that the robots don't have to do in-hand manipulation. For example, in industry, the objects are presented to the robot such that it can simply pick up an object and place it in an assembly. The robot doesn't have to do regrasp. The job of regrasp is done by the support systems around the robot, and then the robot can simply pick and place the objects. So this limits the scope of automation, and when we envision robots going into flexible manufacturing settings, or even in our homes or any unstructured environments, the need for in-hand manipulation becomes more and more critical. So with our work on extrinsic dexterity, we showed that simple grippers, dramatically simpler than human-like grip hands, can do in-hand manipulations reliably if they can use these external resources. Since then, actually many groups have proposed planning and control methods to do in-hand manipulations using dynamics motions and gravity. I'm particularly interested in one set of extrinsic dexterity where object in the grasp is manipulated by external pushes. These external pushes can be from the extra fingers of the multi-finger gripper, or if we have two-arm robot, the second arm can push the object in the other arm. If we have very simple system, if we have neither of these, the robot can simply push the object against the environment to regrasp it in the hand, as we see in this video and also in the first video we saw. So in the rest of the talk, we'll focus on how we can model the mechanics of these prehensile pushes and use them for planning and control of in-hand manipulations. In our experiments, we saw that to regrasp an object, the robot pushes an object against a fixed environment. In our modeling and simulation framework, we sort of picture a mirror image of it. We assume that an object is grasped in a gripper that is fixed in the environment, and there are these virtual pushers with full mobility that push the object from different sides. So moving the robot is same as moving these virtual pushers. So planning a robot motion will be same as planning the motions of these virtual pushers that can push the object from different sides to regrasp it. So with this representation of the system, we'll focus on how we can model the dynamics of prehensile pushing. In the first approach we consider for this dynamics modeling is formulating the prehensile pushing as a general rigid body dynamics problem. The key part in dynamics formulation is actually modeling the force-motion interactions at contacts. In general, the contacts between the object, fingers, and the pusher, they can be point, line, or patch contacts. We'll model them as set of point contacts which move together under rigid body constraints. So a set of point acts as a single patch contact. The forces and motions at these each point contacts will follow a certain set of constraints. For example, the normal force at the contact will be non-zero only if there is non-separation at the contact. It will be zero otherwise. So that can be modeled as a complementarity constraint. We'll assume Coulomb friction model at the contacts. So the friction at the contacts will be such that if the contact is sticking, the force at the contact will be inside the friction cone. And if the contact is slipping, the force will be on the boundary of the friction cone. This is another complementarity constraint. Moreover, when it's slipping, the direction of friction force should be opposite to the direction of sliding at the contact. This comes from maximal dissipation principle. On top of all these constraints that model the force-motion relationship at micro level at contacts, the dynamics also has to follow Newton's equation at high level. Newton's equation will basically govern the motion of all these objects under the effect of all these forces. So when we combine all these constraints together, the dynamics problem for prehensile pushing becomes mixed nonlinear complementarity problem. Nonlinear complementarity directly comes from these nature of complementarity constraints, and mixed because of these additional equality constraints. We solve this dynamics problem as an optimization problem by minimizing the complementarity constraints to 0 subject to rest of the constraints. We use interior point methods in MATLAB. A solution to this optimization problem, or the dynamics problem, allows us to predict the motion of the object for given instantaneous motion of the pusher. Or the other way, it also allows us to predict the motion of the pusher required for instantaneous desired motion of the object. So building upon this dynamics formulation, we develop a sampling-based planning framework to generate long, continuous pushing actions for in-hand manipulations. Given an initial grasp and a goal grasp, we expect our planner to generate a sequence of pushes that can move the object from a start pose to a goal pose, as we'll see in a minute. One of the key challenges when planning such long pushing strategies is actually to understand which of these pushes are dynamically feasible and which of them are not. And that's where actually our dynamic solver comes into picture at low level. And at high level, we use a sampling-based planning framework to sample different grasp configurations, which uses this low-level dynamic solver to know which of these grasp configurations can be reached. If the sample grasp configuration can be reached, it's added to the planning tree, and if it's not, it's rejected. So using this dynamic solver and high-level planning architecture, we can build a tree of grasps where a path in this tree provides a pushing strategy to move the object from a start pole to the goal grasp. For this high-level planning architecture, we actually use previous work called TRRT star planner. It allows us to guide the exploration of the tree towards the grasp pose, and also allows us to reduce the number of pusher switchovers from one side to another if it's possible. So we'll see a couple of examples of regrasp strategies generated using this planner. So in this first example, the goal is to offset the object horizontally in the grasp. The friction conditions and the grasping forces are such that if the robot decides to simply push the object from side, the object will slide down as it moves sideways. So in that case, our planner comes up with a strategy that decides to push the object up first so that it can compensate for the downward sliding of the object that's going to happen in the later stages when the object is pushed from the side. We can see from this video that using this strategy, a robot can grasp or regrasp the object offset to the center horizontally in the grasp as we wish. In the second example, we show that how our planner can reason about concatenating small pushing actions for a long term and then generate complex in-hand manipulations. In this case, we want to rotate the spherical object about the vertical axis by 90 degrees. But the robot doesn't have enough control to rotate the object in grasp using just the point contact at the bottom. So in that case, the planner comes up with this rolling strategy where the roll pitch all change during the manipulation, but towards the end, roll and pitch go to 0, and we get net rotation about the vertical by 90 degrees. So this shows how a dynamic solver, a good dynamic solver, with a sampling-based planning method can allow us to generate complex in-hand manipulations. So this looks all good, but the limitation here is that the planner takes up to tens of minutes, and in some cases, few hours to generate these pushing strategies. And the reason here is because to generate these planning trees, planner every time has to sample different grasp configurations, and has to query the reachability of these sampled grasps. If the dynamic solver that's going to solve for this reachability is not efficient, as in our case, it takes, our dynamic solver takes 2 to 4 seconds to solve for each of the sampled grasps, to solve for their reachability. And in that case, it affects the planning time very badly. So to address this limitation, we dug a bit deeper into the mechanics of pushing, and then we developed efficient formulation to understand the reachability for pushing tasks. Especially, we show that we can estimate set of feasible motions in the form of motion cones. And using these motion cones as directly as reachability bounds in the configuration space, we develop fast in-hand manipulation planner. So in the next few slides, we'll discuss the mechanics of how we compute these motion cones, and then how we can use them for planning and control strategies. So in the thesis, we present analytical approach to compute motion cones for planar in-hand manipulations. Here I'll focus mainly on graphical intuition of how these motion cones arise. So let's consider a representative example where an object in a parallel jaw grasp is pushed against a line pusher. The configuration space is 3-dimensional because the object can translate in the XZ plane and rotate about the y-axis. We'll model the force-motion relationship at finger contacts with limit surface, which is basically integration of friction wrenches over finger contact area. For an external wrench on the boundary of the limit surface, the object slides in the grasp, and the direction of sliding is given by normal to the limit surface. We'll model the force-motion relationship at pusher contact with generalized friction cone. It is basically a wrench representation of individual forces that can appear at point pusher contacts. So with these contact modeling tools, we can go back to our prehensile pushing example, where we are pushing the object against a line pusher. Now we know how we can model the forces at pusher, at fingers, and also the gravitational wrench. Then finding the motion cone it basically boils down to solving the motion equation, that is Newton's force balance, for a set of all these forces. Graphically, it's same as basically intersecting the combination of pusher wrench and the gravitational wrench with the boundary of the limit surface. That defines a subset of limit surface for all possible object motions. When we draw normal to that intersection set, we get set of object motions that the pusher can induce on the object using friction contact. This set is a cone defined by low curvature surfaces, and this is the motion cone. We propose polyhedral approximation of motion cones for their efficient computation. So in a sense, motion cone can be viewed as motion space representation of friction cones. So similar to friction cones, only using motion cones, pusher can exert only the motions that are inside the motion cone. If we apply a pusher motion that's outside the motion cone, there will be slipping between the pusher contact and the object will move only along the motion that's on the boundary of the motion cone, very similar to how friction cones behave. So first, before going for how to use this motion cones for planning, we'll see how our analytically computed motion cones are reasonable, how well they capture the physics of these pushing actions. To do that, we carried out thousands of pushing actions in different grasp pusher configurations with this manipulation setup. So we'll consider one of those experiments. And this is the motion cone computed for that particular grasp pusher configuration. So during the experiments, we sample random pushing directions. And using those pushing directions, we push the object against the fixed pusher. We also observe the slipping between the object and the pusher so that we know for which of these pushers there was slipping at the pusher and for which of these pushes there was no slipping at the pusher. If the contact between the pusher and the object sticks, we'll plot that as a black dot on that motion cone. And if it slips, we'll plot it as a gray dot. So theoretically, motion cone should be able to capture all the pushes for which the pusher contact sticks to the object. We can see from that figure that most of the sticking pushes actually lie inside the motion cone, and most of the slipping pushes, they're outside the motion cones. Overall, we observe that analytically computed motion cones capture physical pushing actions, so feasible pushing motions, with 80 to 90% accuracy. Also, if we observe carefully, the wrongly labeled pushes are very close to the boundary of the motion cones. So that could be because of minor variations in the physical parameters during the experiments. So if you remember, the main motivation for developing motion cone was to exploit the reachability knowledge for planning purposes. So to do that, we'll go back to our two-step planning framework. We'll keep the same TRRT star-based high-level planning architecture, but instead of solving the inverse dynamics problem for every sampled grasp, we'll just check whether the sampled grasp is in any of the motion cone at the nearest node. If the sampled grasp is not inside the motion cone, we'll simply project it on the motion cone, and that gives us close to the sample but reachable grasp configurations that we can add to the tree. So using this propagation mechanism, our sampling-based planning framework again generates a tree of grasps which are connected by dynamically feasible prehensile pushes with their motion cones to go with it. Again, path in this tree provides a pushing strategy to move the object from a start configuration to the goal configuration. We'll see a couple of examples of regrasps generated by using this planner now. One of the big difference, you'll see that the planner generates all these regrasps in a fraction of a second. And this is including computation of motion cones. Also, because motion cones provide the knowledge of all feasible actions, the planner can use that knowledge to take more direct strategies towards the goal pose. So in this example, we can see that the planner can also reason about the non-convex shape of the object and then figure out the pushing strategies to achieve the desired regrasp. So the big difference we see from this motion cone planner and our previous method is the speed improvement we get for planning these pushing strategies. And the speed improvement is mainly because of two reasons. One, because we restrict the planner to travel to the interior of the motion cone, it limits the contact mode at the pusher to sticking contact. This allows the planner to avoid the combinatorial aspects of deciding between sticking and slipping at multiple contacts. That's one reason. And second, as we discussed before, motion cones allow the planner to know what are all possible object motions it can do at a given instance. So that can be used for very fast propagation for planning tree. So this is all good that now we have a framework that can generate in-hand manipulation strategies in a fraction of a second. But again, limitation here is we always assume the knowledge of physical parameters of the system. We assume the knowledge of friction at the contact. We assume the knowledge of grasping force, object mass. But in many of the cases, what can we do if we have some uncertainty over these physical parameters? So in our recent work, we explored different methods that can allow us to handle the uncertainty in these physical parameters of the system. In the thesis, we have proofs and theoretical guarantees for generating conservative approximations of motion cones and using them for planning in-hand manipulations that are robust against uncertainties in pusher friction, finger friction, grasping force, and even mass of the object. So even if we have a robust pushing strategies, sometimes what can happen is the object can get perturbed during the manipulation. So how can we handle those cases? To handle such external perturbations and still successfully regrasp the objects, we develop a feedback control framework using motion cones. And in the next few slides, we'll discuss how this feedback framework can allow us to robustly execute in-hand manipulations. Before doing that, let's look at how this, one of the examples of this controller showing how it works. So here we can see that the controller responds to me poking the object and generates pushing strategies and executes them to get the object back to the center in the grasp. To understand how this control framework works, we'll look at just a sample cartoon of a plan generated by our planner, the motion cone-based planner. So different colors here just indicate different pushers used to move the object. For example, we can say the green color indicates the side pusher was used, and blue color indicates the bottom pusher was used. So during the execution, the controller generates local pushing strategies to keep the object pose close to this originally generated plan. To do that, based on the current pose of the object, we select a k-step path from the original plan. We define the cost function as pointwise distance metric from this sampled reference path. To follow the pushing dynamics, we'll constrain the pushing motions between two knot points of this control sequence to be inside the motion cone of the first motion, inside the motion cone of the first point. So for example, the motion between P2 and P3 has to be inside the motion cone at P2. To keep these constraints linear, we'll assume that the dynamics follows the motion cones computed at this reference path. And of course, the start of this controller has to be from the current pose of the object. So with these linear constraints and quadratic objective function, generating this local corrective pushing strategy becomes a quadratic optimization problem, which we can solve very efficiently. We can see a few examples where this controller shows how it can handle external disturbances and noise in the system. So in this example, the robot wants to grasp the object at the center, as it's doing now. If we move the object away from the center, it will generate a prehensile pushing strategy using the motion cone-based planner that we discussed before, and then execute that strategy using the controller we just discussed. We are not going to add any disturbances in this example. So this example shows that we can get the object back to the center as we wish. This plot just shows the planned expected motion of the object in the grasp and what we see during the experiments under the active controller. We can see that the actual pose of the object is not exactly how the planner expected it to be, but the controller always keeps it close to the original plan and moves the object to the goal grasp eventually. In this second example, the basic idea is the same, that the robot wants to grasp the object at the center, but will move the object after the robot registers the pose for planning. So the controller has to start its execution from a pose different than what the planner took for planning the pushing strategy. I can explain it in this better in this plot. We can see that the expected pose of the object in the grasp by the planner is completely different than what the controller has to start from. The controller starts from very far away from the plan trajectory, but it keeps the object pose moving towards the original plan and eventually gets it to the goal pose. In the third example, we'll show that this controller can allow us to handle external disturbances and then to achieve the desired regrasp. Here we want to regrasp the object to this green pose under some external disturbances. So as the robot is trying to regrasp the object, I'm moving the object in the grasp, and the controller is coming up with corrective pushes locally to get the object back to the originally planned strategy and back to the desired regrasp. So this is again the plot of the object motion from the previous run. We can see, so the red arrows there shows the change in the pose of the object when we apply external disturbances. We can see that the object moves significantly in the grasp when we apply those disturbances, but the controller is able to handle those well and keep moving the object towards the originally planned strategy and get it to the goal grasp. Okay, so to conclude, what we saw in this thesis is if we allow robots to use gravity, dynamic motions, and external contacts, they can effectively manipulate objects in hand, even with simple grippers. We focused on one of the mode of extrinsic dexterity, where the object is manipulated by pushing against the environment. We further developed planning and control methods for this particular mode of extrinsic dexterity. We studied the mechanics of pushing actions and developed efficient models to capture the reachability knowledge for these pushing actions in the form of motion cones. We showed how we can use motion cone for fast and robust planning, and also for in a feedback control for executing the pushing strategies in a very robust fashion. To conclude, I can say that I believe that if we have strong and efficient planning and control methods that can allow robots to do in-hand manipulation with extrinsic dexterity, simple robots with simple grippers can not only grasp the object, but start using them at the desired applications. So this was the overall thesis that I enjoyed working on for last few years. And before going to questions, I would like to acknowledge few people without whom it won't be possible for me to be here, enjoy doing what I do. So to start with, thanks a lot, Alberto, for continuous support and guidance. You have always provided encouragement for trying new ideas, getting stuck, keep pushing, and then learning something new. So thanks a lot for that. A big thanks to everyone in my committee, Professor Hogan, Professor Tedrick, and Professor Mason, all of whom have motivated some part of this thesis. I'm grateful to Professor Mason, who let me took my baby steps in robotic manipulation when I started my master's at CMU. Professor Hogan's comments on exploiting our unfair advantage of knowledge of mechanics allowed us to explore the ideas of motion cone more and see how we can use them for efficient planning and control. And of course, Professor Tedrick's advice on thinking about robust planning and control has made this work a more complete work. So big thanks to all of you. The time at MIT won't be as enjoyable as it has been without each and every member of the M-Cube. So big thanks to you guys. I feel very fortunate to be in this lab and call a few of my best friends which work alongside me. Last but not least, I would like to thank my family, my parents, my sister, for their constant love and support. Enjoying this experience of being at two of the best schools, CMU and MIT for robotics, has been a very cherishing moments and very enjoyable experience. And I couldn't have done that without the constant support of my family. So I would like to thank them for that. So with this, I'm open for questions and any comments on this work.
Thank you for the great presentation. So when I was looking at your videos, I was thinking you kind of assume that the contacts are fixed. They're available to the robot. There's one on the side and there's one on the bottom.
Mm-hmm.
You could play the inverse of this game and say, this is a design problem now. Which fixtures do I pick and where do I put them? Like, conceivably, this whole thing could be done with just one diagonal one, maybe. Is that possible? So do you have any thoughts on, rather than doing this as a planning problem, solving as a design problem?
Yeah, so yeah, that's a very interesting question. And the funny thing is, that's what I always wanted to do, like how we can design the environment around a robot to make these actions more efficient. I didn't get enough time to get to that stage, I guess. But yeah, that's a very nice direction to look at. So the focus of this thesis so far has been on seeing how we can use standalone grippers and robots and use them for in-hand manipulation without any custom hardware. So we tried to focus on that. But yeah, I guess there are a few applications where we have the opportunity to design the environment. And in those cases, yeah, it's a very interesting problem to think about how we can design these features or even place them, as you said, for better in-hand manipulation. That can potentially make the planning of these actions more simpler and may provide more scope for in-hand manipulation.
I'll try to think of the best way to formulate this question. So it seems as though in many of the use cases that you've demonstrated here, it involves essentially what is planar manipulation, with the exception of the sphere. What would need to be done to generalize the framework that you've built to more general 3D, I guess, rotations and translations?
Yeah, so the first modeling approach we considered with the MPC-based dynamics modeling, it's actually general 3D manipulation. And the planning actions we saw with the sphere, that's also planned in 3D. But when it comes to efficient modeling and then using these ideas such as motion cones, yes, the work, even in literature, has been limited to planar manipulations. And there are multiple reasons why it's difficult to extend these ideas, such as motion cones, to 3D manipulations. For example, the limit surface itself is limited to planar contacts. It's hard to generalize that concept for complex curved contacts or in 3D manipulations. But yeah, it's an interesting problem to think about how we can generate efficient dynamics model for more general set of systems. I guess one of the work I can point you to is some of the recent work from Professor Tedrick's lab about how we can generate these reachability maps for more general class of manipulation actions. That's one way to go about it.
So your reachability motions, even in the plane, are approximate, right? So I think in force space they're exact, but because you have to interpolate a little bit over the motion, your Jacobian changes, that's a nonlinear change. It's no longer perfectly represented by a polyhedral cone, right?
Yes, so the approximation comes from our polyhedral approximation of the motion cone.
Yep, but it would have to be it would be hard to not approximate that.
Yes, the computation will take a lot of time because if you want to compute the true motion cone, basically you will have to sweep the boundary of this wrench cone and compute this curved motion cone. We avoid doing that. We just say compute the motions at the four corners, and we'll assume the polyhedral approximation to be our motion cone. Yes.
So the question is, does that impact your completeness of your algorithm? Do you worry about, I mean, probably not in this environment, but could there be a plan that exists that you don't find because of your approximate motion cones?
Yes, it's possible because we'll miss the motions which don't fall in this polyhedral approximation, but are part of this curved motion cone. So so using motion cones, it's a bit better than using the MNCP-based approach, because solving the MNCP as an optimization problem, that itself is, we don't have guarantees for solution there. But with motion cone, at least we have analytical solutions. But because of the approximation, we may miss some of the motions that otherwise are possible. Yep. It's in the velocity space. Into drift problems? I didn't see that. Yeah. And those velocity constraints, they are another reason why the problem becomes mixed. So it's particularly there when you have these patch contacts in general.
This idea of the motion cone, is there hope to generalize it to more complex systems, grippers? And if not, what's the limitation there? What prevents us from doing it?
Mm-hmm. Yeah, so it's not necessarily confined to any gripper or anything, but as I mentioned to Orion, the current development in the thesis is limited to planar manipulations. So to planar finger contacts and to planar pusher contacts. So if we think about extending the idea of motion cone to 3D manipulations, first of all, we'll have to have a notion of somehow capturing this grasp resistance in 3D. We were able to do that with limit surface because we are limited to planar manipulations. But I think that would be the starting point of how we can think about capturing the grasp wrench in 3D and then moving. If we can do that, then generating motion cones for 3D manipulations is possible. There has been some recent work on generalizing limit surfaces to curved patch contacts and for 3D scenarios. So theoretically, we should be able to compute motion cones. It won't be computationally efficient, though. It won't be easy to solve those equations in closed form or analytically.
So you're talking about if the complex surface is in 3D. So let's say you all have planar surfaces, but they are in 3D.
Not really, because all the examples we saw, they are working in 3D, but the contacts are.
Do you ever make a break in your motion cone?
No, so there is no. So motion cones are not restricted to sticking contacts. So motion cone just tells you that these are the motions that you can impose on the object. The way we use motion cone is by confining the planar to be inside the motion cone, and that's where we are restricting to only sticking mode. But yeah, in the planning framework, we don't allow the pusher to stick or slip. It's always confined to sticking contact.
I wanted to ask Matt to see if he has. Matt, do you have any questions?
Sure. Can you hear me?
Yes, we can.
I follow up on that question about the approximation of the motion cone. Mm-hmm. And I was wondering if you thought about trying to break it by, like, designing what's the worst possible limit surface and the worst possible configuration. Can you design a problem that's in some sense the worst case for that approximation?
Yeah, so yes, we actually did it. so the curvature of the facets of the motion cone, it depends on the ratio of the grasping force and the gravitational pull on the object. If the grasping force or the friction force at the fingers is significantly larger than the gravitational pull, the curvature of the facets of the motion cone, they are smaller. That's again true if we have a large offset between the CG and finger contacts. So if we grasp the object with low grasping force and far away from the CG of the object, the curvature of the motion cones will be very high, and you can visually see that the polyhedral approximation is just very bad approximation for those motion cones.
Wouldn't large rotations also be problematic if you're away from the center, if your center mass is away from the center? But any large, I mean, the rotations in general is what gets us in most of these contact mining problems, right? Is that they have strong nonlinearity, non-convexity. And I think in your case too, the Jacobian would go through, if the Jacobian changes a lot, then your polyhedral approximation is fast, right?
Mm-hmm. Yeah.
Just going more into this adversarial topic, could you possibly discuss like if you had an ideal object that you wanted to manipulate, what would the easiest object to manipulate be, and like what would the hardest be, and also like what would a very hard task be, and like what would a very easy task be in your framework?
Mm-hmm. Okay, so easy object is probably objects with planar facets, so that we can have parallel jaw grasps, planar contacts, all the assumptions that we made in Thesis are valid. So those will be good objects to handle with. The difficult objects are probably curved objects where the contact geometry can change very frequently as the fingers move over the object. And also the objects which have very non-convex shapes, we may lose grasp on those objects. So those would be the hard objects to deal with this framework. Difficult problems and easy problems.
Let me maybe rephrase Orion's question, because I think that he was asking for something slightly different. Like, let's assume that we are restricting ourselves to just objects that fall within the assumptions that you've made in your thesis, mm-hmm. right? So planar, what is an easy object and what is a difficult object that you might be able to solve but might be affected by the curvature or by, mm-hmm. Like I'm assuming, for example, an easy object would be a cylindrical object where you're just grasping on the sides of the cylinder, right? It's symmetric in all directions. The center of mass is roughly at the geometric center of the object. What would be a difficult object for your planner to come up?
An object with very off-center mass would be difficult to handle with, or objects where mass changes over time is going to be almost impossible because we'll have to compute the dynamics at every instance. Yep, that's a good, interesting question to think about. Yep.
Wait, 1 second. Let me give the mic.
So how about the object that is very soft?
Yes. Yeah, that's.
It must be very difficult.
I forgot to mention that. Yeah, that's another big assumption of this work, that we assume that objects, contacts, all are rigid contacts and mm-hmm. rigid objects. So if we are dealing with soft objects, it's going to be difficult.
But you think you still can solve this problem when you're grasping a soft object with this method?
I think easy answer is no. I don't think these methods extend to soft contacts or soft objects. Maybe using other modes of extrinsic dexterity, using gravity and dynamic motions could be more useful there, because the biggest thing that prehensile pushing, or pushing the object against the environment, it derives, or it relies on the rigidity of contacts for precise manipulation. If we don't have rigid contacts or rigid objects, maybe other modes of extrinsic dexterity could be better.
Okay, thank you.
Any other questions? All right.
I think the planner is assuming that the friction property is known.
Yes.
And do you consider, like, did you consider, or do you plan to consider estimating the friction property online?
Yeah, no. The answer is no, but yeah, that's very, we thought about doing that, but didn't happen. Is, yeah, how we can estimate the physical parameters of the system as we are pushing the object in the hand. That's something very interesting to look into. Yeah, it's more like active exploration for system ID.
Matt, any other questions?
No, thanks.
All right. Anyone else? If not, I think we'll thank Nikhil.
Thank you.